We've all done it. Typed a question into a chat box and boom, an answer appears. It feels like magic, right? But have you ever stopped to think about what it takes to actually build the machine behind that magic? It's a whole different universe from just using it. So today, we're going to pull back the curtain and look at the real blueprints of the machine itself. And let me tell you, the gap between a user and an architect is vast. On one side, you've got the AI user. They're focused on results, things like prompt engineering and API calls. It's kind of like ordering from a really fancy pre-made menu. But on the other side, that's the AI architect. They're in the kitchen, redesigning the stove for maximum efficiency. They're dealing with things like kernel-level optimizations and building from first principles. Today, we're stepping into that kitchen. So where does an architect even begin? Well, it's not with some high-level library or a quick tutorial. It starts at the absolute bedrock. It all comes down to a philosophy called the FPR technique, and it's all about escaping that black box so you can truly understand what's happening at the most fundamental level. And this technique is a super clear three-step process. First up, the fundamentals. We're talking the raw math that makes everything tick. Second, the practicals. This is where you translate all that theory into actual working code. And finally, you have research, getting your hands dirty with the latest scientific papers, maybe even reproducing them. Because see, the whole goal here is to know why something works, not just that it works. Big difference. And when we say fundamentals, we really, really mean it. This isn't just some abstract theory you learn in a class and forget. You can see right here how linear algebra is the tool you use for something called dimensionality reduction, and how calculus is literally the engine that drives optimization. This is the solid ground that all of modern AI is built on. If you don't have this, you're basically building on sand. Okay, so once you've got that solid mathematical foundation, then you can start architecting the thinking machines themselves. This is where we get into the actual blueprints for the most powerful AI models we have today. And at the heart of pretty much everything is this revolutionary idea, self-attention. This is the secret sauce inside the transformer architecture. It's what lets a model look at a whole sentence and figure out which words are most important to which other words. It's how AI finally learned to understand context. And honestly, it's the one innovation that unlocked this entire generative AI revolution. But, of course, that incredible power comes with a pretty steep price tag. The complexity grows quadratically. What does that mean? It means if you double the length of your text, the amount of computation you need doesn't double, it quadruples. For long documents or articles, this just becomes impossibly slow and wildly expensive. It was a massive bottleneck. So how do the engineers get around this? With a truly brilliant architectural trick called Mixture of Experts, or MOE. The idea is genius. Instead of having one giant model trying to do all the work, you have a smart router that sends each little piece of information to one of many specialized expert models. It's like having a whole team of specialists instead of one overworked generalist, and it is way, way more efficient. All right, so you've designed this massive, brilliant model. Great. But now you've got to face what engineers call the last mile problem. How do you make this thing actually run fast enough and cheap enough to be useful in the real world? This, my friends, is where all that beautiful theory meets brutal reality. And there's this fantastic quote that really captures the challenge. It describes model compression as being like neurosurgery on AI brains. Think about that. It's this incredibly precise, delicate process of manipulating the model's structure to slash its resource usage, sometimes down to less than 10% of the original, all without losing its intelligence. So what's the biggest target for this so-called neurosurgery? Well, it's a little thing called the KVL cache. The easiest way to think about it is as the AI's short-term memory. As it's generating text, word by word, this memory just grows and grows, and it eats up a massive amount of that precious GPU memory. And this leads to something engineers call the cache trap, and it's frankly terrifying. Let's say you've got a top-of-the-line H100 GPU, packed with 80 gigs of VRAM. Just loading a big 70 billion parameter model can eat up around 70 of those gigs. So what's left for the AI to actually think with, for that KV cache to grow? A tiny sliver. Barely anything. Suddenly, even your most powerful hardware is pretty much useless without some seriously smart software optimization. Solving this trap means an architect has to make some really tough strategic choices. You have to pick your weapon. See, there's no single best tool for the job. If you just need to get something into production fast, VLLM is an absolute workhorse. But if you need to squeeze out every last drop of performance, you might need to invest weeks of expert-level effort into something like Tensor RTLM. It always comes down to a trade-off. Now, let's zoom in on just one of these crazy optimizations, FP8 quantization. This is all about using smaller, more efficient ways to represent numbers. But what's really fascinating here is that you don't just use one type. You actually use two different kinds. You use one called E4M3 for the forward pass. That's when the AI is generating an answer because you need really high precision. But you use a different one, E5M2, for the backward pass, when the AI is learning because you need a higher range to keep things stable. It's this level of insane detail that makes all the difference. And what's the result? What's the payoff for all this painstaking engineering? Well, with innovations like multi-head latent attention, you can get a 3.2 times speed up in inference. Now, that's not just a small improvement, that is a total game changer for deploying these models at scale. But speed is only part of the puzzle. The ultimate goal, the real holy grail, is moving beyond just generating plausible-sounding text to something much, much deeper. Actual cognition. Actual reasoning. This is the final frontier. And believe it or not, there's actually a recipe for it. This blueprint shows the incredibly careful process behind today's top reasoning models. It's not just one big training run. It's a careful, multi-stage process that starts with pure reinforcement learning, just to get the model to even try to reason. And then it carefully layers on fine-tuning and stabilization before a final polish at the end. A key piece of that process is a technique called GRPO. And I love this. Think of it like a debate club for the AI. Instead of a teacher marking an answer as just right or wrong, the AI generates a possible answer and then compares it against a whole group of other potential answers. By learning what makes one answer better relative to the others, it learns to build much more complex and robust chains of logic. So what's the big takeaway here? The modern AI architect is a true hybrid, a jack of all trades. They have to be a mathematician, digging all the way down to first principles. They have to be a systems architect, designing these elegant and efficient models. And finally, they have to be a performance engineer, relentlessly optimizing those designs for the messy, complicated real world. It's the fusion of all three that truly builds the future. And that brings us to one final thought. We've just gone on this incredible journey to see the human ingenuity it takes to build a machine that can reason. So, as AI gets better and better at solving these complex last-mile problems for itself, what becomes the new last mile for us, for human ingenuity? What's the next great problem for us to conquer?